this lesson, we'll dissect a functional concept, the Y-Combinator. So this will be a fairly theoretical lesson and it will involve a good amount of mathematics to it. So I suggest you take it slow and pause the video whenever you feel overwhelmed and reflect upon what you have seen so far. The benefit of this lesson is, once you fully understand how the Y-Combinator works, you won't have much problem in understanding any functional programming concept that's thrown at you. But before I begin, I want to emphasize several things. First and foremost, functions are just mappings. They take a value and they map that value into a new value. And while watching this lesson, keep that fact in the back of your head. And secondly, Y-Combinator has a fairly convoluted logic. So as always, while following along with me, pause this video frequently, take notes if you want, and try to replicate what I am doing in your development environment as well. And third, Y-Combinator is a mathematical concept, so showing how it works is no different than proving a mathematical concept or a mathematical theory. So we'll start by laying out small basic building blocks, and step by step we'll show how and why the Y-Combinator works the way it works. And although it's not strictly required, you might find it easy to follow this lesson if you are familiar with the concepts like recursion, anonymous functions, immediately invoking function expressions or IIFEs, closures, function composition, and higher order functions. So knowing these concepts will prove themselves useful in this lesson. So if possible, I'd recommend you briefly overview these concepts before watching this video. With that said, let's begin. We'll start with how you can write the Y-Combinator function in JavaScript. Our combinator function y will take a lambda expression as input and apply a function to itself and return the resulting function. The function we apply to itself in itself takes another function and applies that function to itself and passes the return value of that into our lambda expression as an argument and eventually returns what that lambda expression returns. So what's a lambda expression? Without diving into too much mathematical rigor, for all practical purposes, you can think of lambda expressions as just functions or as anonymous functions. So whenever I say lambda, replace that word with function in the back of your mind. And if that's the first time you are looking at this Y-Combinator equation, it may look a little difficult to decipher. So just bear with me, I will dissect it and explain how it works piece by piece. So what makes the Y-Combinator so special? It's because Y-Combinator is a fixed point combinator that you can use to define recursive functions in languages that may not support recursion. But what is a fixed point combinator, you may ask? This Wikipedia article pretty much sums it up, but it might be too much information to look at all at once, so I'll try to simplify it here. But for that, we will need some extra definitions. So Y-Combinator is a fixed point combinator. But what is a combinator in the first place? Well, a combinator is just a special function that takes a function as an argument. Formally speaking, it's a function with no free variables in it. But informally, you can think of a combinator as a function that puts together, that is to say combines, pieces of programming logic to form a more advanced or a higher order logic. But what the heck is a fixed point? Well, the fixed point of a function is a mapping to itself. So if c is a fixed point of function f, then fc will be equal to c. So visually speaking, fixed points of a function will be the intersection of that function with the identity function. Y-Combinator, being a fixed point combinator, will return the fixed point of any function when you apply it to the function. I don't know you, but this looks pretty much like recursion to me. We are recursively applying a function to itself as you see here, and that's why Y-Combinator can be used to formally define recursion as we'll see shortly. To demonstrate this, I'll take the y function and create two higher order recursive functions, one for calculating the factorial of a number and another for calculating the nth Fibonacci number. The Y-Combinator is like a factory or some sort of a generator, and if you conceptually consider these functions as template or abstract functions that describe a recursive algorithm, then when you pass these template functions to y, you'll get the concrete functions that implement the actual recursive logic. So when we call factorial 10, we'll get 3,628,800, which is equal to 10 factorial. And when we call Fibonacci 5, we'll get the fifth Fibonacci number, which is 5. And that's all because of the equation y of f equals f of y of f holds true. But why is that so? To show that the equation is indeed true, it will be easier to use the function's lambda notations. So when written in lambda form, this equation will turn into this, where lambda represents a function and this dot operator means function application. So this is equivalent to this. So if it feels confusing, pause this video and take your time to familiarize yourself with the notation, but the gist is these two expressions are identical. And I'll flatten this expression to preserve some vertical space. And now let's pass your y function a parameter g, similar to how we generated the concrete factorial and Fibonacci functions out of fact and fib functions by passing them to y before. So the equivalent expression will be this, taking this entire expression and applying g to its right-hand side. And that would mean take this part and replace f with g wherever you see f, which mathematically is called a beta reduction in lambda calculus. Now, this in itself is an expression, and we can do the same beta reduction again, taking this and replacing wherever we see x with this expression. So each of these x's will be these expressions, so let's do the replacement. Well, actually everything you see inside this parentheses here is yg, and you can realize that it's true if you look at this second line here, which also completes our proof that y of f is equal to f of y of f. So let's try to come to a similar conclusion using JavaScript as well. But before that, we'll have to examine a few building blocks, which I'll call lemmas. Our first lemma is a JavaScript function can take a primitive value like a number or a boolean or a date time and return another function. To exemplify this, let's have a power function that takes a number and returns a function that calculates the nth power of that number. It might be clearer to see if we write this in expanded notation like this. So we can, for example, create a 2 to the power function by calling power with 2. And we can call 2 to the power on any number to raise 2 to the power of that number. So 2 to the power 3 will return 8 as expected. Our second lemma takes this one step further, and it says a JavaScript function can take a function and return another function, which is also called higher order functions. To demonstrate this, let's have a simple square function that does exactly what you think it does. It takes a number and returns the square of that number. So let's have a log result function that takes any function and returns a function that takes a number and logs the result of the function applied to that number. And again, it might be easier to visualize it when we use this extended notation like this. So we can create a print square function that will be log result square, and when we call print square 10, it will log the square of 10, which is 100 as expected. And here comes our third and final lemma, which is actually a lambda calculus phenomenon. F of n is equivalent to the lambda form of f, which is x goes to f of x applied to n. In simple terms, this means that you can replace a function reference with its anonymous function representation and vice versa, and the outcome will be the same, which is nothing surprising, but it's useful to keep that in mind as well. And as a concrete example, square 4 is equivalent to executing a function that takes an argument and passes that argument to square, which is the lambda form of square, and then passing 4 as an argument to that combination like this. So when we run it, we'll get 2 16ths logged to the console as expected. So after introducing these building blocks, let's do something practical and write a recursive factorial function. And when we call factorial 6, for example, we'll get 720, which is the factorial of 6. Now let's assume that a function is not allowed to call itself directly. So if we cannot call a function within itself, how can we do recursive logic? Well, we can pass a function as an argument and call that function instead, like this. So it's almost the same logic, but instead of calling factorial, we'll be calling f, and since f assumes two parameters, we'll add a second argument to here, giving f to itself as a parameter as well. But how are we going to provide this f, if you ask? Well, since factorial is a reference to a function, it's basically a variable. There is no reason we cannot pass it as an argument to this function as well. Sure, it is weird and it's arguably useless, but it will still work, as we'll see. So when we call factorial 6, we'll again get 720 as expected. I know that's a little convoluted, but I have a point, so bear with me for a while. Also, I'll slightly modify this function to make it fit better to functional paradigms. So instead of the function taking two arguments, we'll have a function that takes a function and returns a function with a lesser degree of freedom like this. So these two expressions work similarly, and as an exercise you can try to prove it yourself, but intuitively it should be easy to see, I guess. So instead of calling factorial 6, we'll call factorial of 6 like this, which will again give 720 when executed as expected. So we are applying the same function onto itself, and by lemma 3 we can replace this with its equivalent lambda expressions, as we'll see shortly. But before that, let's look at something interesting. I'll copy my original factorial function here and name it factorial oric. And I can take a list of numbers and map that list to my function, which will return the first 6 factorials in an array. There is nothing fancy in it. So what do you think will happen if you do the same mapping with our higher order factorial function? Well, we'll get an array of functions, which is not quite what we expect. So to get a list of numbers, we'll have to decrease the function's degree of freedom by applying it to itself. So again, from the third lemma, we can take a lambda function that takes a function and returns the same function applied to itself, and pass our original factorial as an argument to that lambda function, as you see here. So the outcome of this expression will be the same as this doubly applied factorial that you see here. And since the new function accepts a number and returns another number, we can map it over a list of numbers and get a list of factorial numbers in return. So let's do that. And yep, we now have the list of factorials of the first 6 numbers. So now let's create our fact function, which will be our factorial template, if you will. And for that, we'll take a function and a number and return this logic actually. I'll just copy and paste it. And the only thing that I'm going to change it will be to replace this doubly implemented f with a single f, and you'll see shortly why I do that. And this big expression will be equivalent to fact of f that takes n as an argument. And again, from lemma 3, this f of f can be replaced with x goes to f of x, and when we run it, we'll get the same list of numbers, which shows that we haven't broken anything. And also in this expression, if we replace this entire expression with an alias, like, I don't know, an arbitrary letter like z, then this expression will be n goes to z of n, which again by lemma 3 is the same as simply using the function z instead. So I can get rid of this two n's that surround this expression, and the result will be the same. And if you are not convinced, you can take a simpler example. Like if a is a square function and if b is a lambda function that uses the square function, then a100 will be equal to b100. That's exactly the same transformation that we are doing here. It's just more letters and symbols, but the logic and the math behind it is identical. But if you don't trust the math, we can always test the new function to make sure that it works. And it works again, and we get the same numbers as expected. So let's extend this function again to make it easier to observe. And finally, we'll increase the order of this factorial function by passing a fact parameter to it like this. And the only remaining thing to be done is to rename this factorial to y and rename fact into lambda expression or LE. And we'll get, guess what? We'll have our initial Y-Combinator function as a result. And the good thing is, since Y-Combinator returns the fixed point of any function, you can use it to create recursive forms of not only factorial, but also any other recursive function as well. So take this higher order Fibonacci template for an example. You can just pass it to y to generate a Fibonacci function. Then I can use the same mapping to map the first 6 factorials and the first 6 Fibonacci numbers. And when I run the code, we'll get the expected results as you see here. And that's also the end of this lesson. To be honest with you, every time I analyze this Y-Combinator expression, I get mesmerized by its mathematical beauty. Or maybe it's just me being a nerd, I don't know. But I hope you liked it too.